I mentioned earlier in this presentation that we would be comparing what's good about the repeated measures design over what's good about the independent measures design. So we're going to start that now. We're going to look at 3 different things that represent the advantages of the repeated measures design, just abbreviated there. So this idea of taking one sample and measuring them twice, there's 3 essential advantages we can get out of that from a research point of view. The first advantage is that we need fewer subjects. If we think about it, if I wanted to make 15 comparisons, 15 scores compared to 15 other scores, if I did this as an independent measures design, I would need a sample of 15 people for one group and a separate sample of 15 people in the other group. I need a total of 30 participants to get that study done. But if I did that with a repeated measures design, I get a sample of 15 people in the first treatment condition, and I'm recycling them. I'm using the exact same 15 people all over again. So to make 15 comparisons with an independent measures design, I would need 30 people. But with a repeated measures design, I only need 15. Now, we know about the connection between sample size and error, so this might sound counterintuitive, but don't worry about that right now. We'll get to this error thing in a second. The main advantage this represents is a real-world advantage. More subjects you need, the more time it takes, the more money it costs, the more slowly you get done. So having fewer subjects is, generally speaking, a faster and less expensive way of getting the job done. And those can be really important real-world concerns. So, and ultimately, people moving them through experiments, you've heard the expression herding cats. It can be like herding cats. Half the number of cats to herd, half the frustration. Secondly, of the 2 methods, repeated measures and independent measures, repeated measures is regarded as the better choice for studying changes over time. If I want to see how something naturally unfolds over some period of time, how your problem-solving skills develop, or how some aspect of your social skills develop over a period of time, the best way of doing that is get some subjects, measure them, and let time naturally pass. Time would be the treatment now, and then measure them some matter of weeks, months, years later, whatever your setup is. You could try to do this with independent measures, get 3-year-olds to compare them to 4-year-olds, but then we've got that problem with individual differences. Are they different because of their ages, or are they different because they're just different kids? So this is generally regarded as the more solid, the more reliable way of getting that job done. Get the sample, measure them, let time take its course, bring them back, and measure them again later. That can come with its own headaches too. Trying to find those people to bring them back can be trouble, but we're talking about methodology here. And so it's regarded as the better choice. You could do it either way, but this is the better one. Now the one we're really going to get into here out of all of these is this last one. Just what we started the day with, this idea of individual differences. It's also what I just referenced a moment ago. If I get 3-year-olds compared to 4-year-olds, if the difference isn't because of the age, because they're different kids, that is individual differences. Well, I get rid of that problem completely here. I get a group of kids when they're 3, measure them, send them home, wait a year. When they're 4, get those same kids back. Again, we're comparing people to themselves as a before and after snapshot, not to a stranger. This, getting rid of this problem, gets rid of a tremendous amount of error. So some of you might have been concerned that if we reduce the subjects, lower number of subjects equals more error. That is true, but we're going to see that that problem is going to be offset and then some by being able to get rid of this error, because it's a type of error. Remember, there's only 2 things that cause scores to change or be different: treatment and error. Those are the only two options we've got. So individual differences is a form of error. What I would like you to do is go to page 317 and look for table 11.4. Obviously pause the video if you need to, but that's what we're going to be working with for the next several minutes. Page 317, table 11.4. When you get to that page, down here, you'll see two sets of data. On the left is data from an independent measure study, two separate samples. And on the right is data from a repeated measures study, same sample measured twice. And if you look carefully, the data is exactly the same. If we look on the left side, treatment condition 1, we've got a John and a Mary and a Bill. And in treatment condition 2, we've got to have 3 different people, Sue and Tom and Dave. And on the right-hand side, we can see it's just John, Mary, and Bill twice. We've used that same group of people both times. But if you look at the scores, they're the same. 18 to 15, 18 to 15. 27 to 20, 27 to 20. 33 to 28, 33 to 28. So the data is exactly the same. The measurements are exactly the same. The only difference between those two tables is the one on the left was done with 2 separate samples, and the one on the right was done with 1 sample measured twice. So what we're going to do, they gave us all the information there we need. We're going to use that information to calculate error, our estimated standard error. So let's work on the left side first. This is basically a review from chapter 10. Well, in order to calculate estimated standard error, we are first going to need pooled variance. So for that data on the left, the first thing we need is our pooled variance. And so remember, our pooled variance is the sums of squares for the first sample plus the sums of squares for the second sample divided by degrees of freedom for the first sample plus degrees of freedom for the second sample. And so it tells us right in the problem, sums of squares for the first group is 114. Sums of squares for the second group was 86. And the degrees of freedom for both groups was the same, 2 and 2. So when we can calculate this, when we compute this, we'll find that our pooled variance for that data on the left is 50 points. Now we can use that to calculate our estimated standard error. So our pooled variance is 50 points, and there are 3 people, 50 points and 3 people in the first sample. And pooled variance is 50 points, and there are also 3 people in the second sample. Remember, two separate fractions there. And when we compute that and round it, what you should find is 5.77. So, based on this data, as an independent measures design, we would end up with an error of 5.77 points. That the differences could stray over 5.5 standard deviations just due to random chance alone. Now, I'm going to write that number up in the corner so that we have it to compare. We know that number is from an independent measures design without labeling it otherwise because we know that's the symbol for error from an independent measures design. Now we're going to look at the right-hand side and we're going to do the same thing. We're going to calculate how much error for the exact same scores, how much error would we have by simply eliminating error from individual differences by using the same sample twice. So of course the first thing we need is our sample variance of difference scores, which is our sums of squares of difference scores divided by degrees of freedom associated with those different scores. And the information in the book tells us the sums of squares is 8. Again, notice the authors didn't put that D subscript on there. You don't have to, except in the hypotheses. I'm just doing this all day for us for consistency, so we remember what we're doing. And the degrees of freedom is only 2, because there are only 3 people in the study. So our variance of different scores is 4 points. And now we can compute our estimated standard error from this data. So again, that's going to be our variance divided by the number of scores, and then number of different scores, and then square root. Well, the variance is 4. The total number of people in the sample was 3. So first 4 divided by 3, then hit the square root button, and we see that answer is 1.15 when we round it. Well, let's look back up here. The exact same measurements, the exact same data. When we use a study that has individual differences in it, 5.77 points of error. When we use the same data for a study without individual differences, where that problem doesn't exist because we're comparing people to themselves, that error drops down to 1.15 points. That's close to an 80% drop in error. So we don't have to worry that our sample size is a little bit smaller. We are more than making up for that problem by running it as a repeated measures design. So that last advantage is a big deal. Now, what we just spent the last few minutes doing is something that will be part of our actual hypothesis test in the next 2 chapters after exam 3. Well, not for both of them, but 2 chapters from now, part of the test will be computing the error due to individual differences and subtracting it out of the test. So it's a little bit of a preview of what's to come there as well. So those are the 3 advantages of the repeated measures design. You don't need as many folks. You don't need as many people. It's better for studying changes over time, and we eliminate error due to individual differences. So next we'll move over to a couple advantages of the independent measures design.